Welcome. This is the last lecture on on iron making. There is the blast furnace iron making, and in this lecture, I will just discuss about some of the new potential technologies for the blast furnace. So, I will first discuss that is how we can improve the thermodynamic performance of the blast furnace to some extent. It can be possible, and what are the potential techniques are available, and people have studied, and also some of them are tested into the pilot scale in the pilot scale blast furnace. And then we will talk about the top gas recycle blast furnace. This is from the point of view of the CO2 emission, reduction in the CO2 emission. And this is the one of the ULCOS project. I will talk about that. And finally, the plastic injection in the blast furnace. Now, the methods for improving the performance of the blast furnace, how we can improve the further efficiency of the blast furnace, thermodynamic efficiency. And here you can see in this diagram, it is basically a FECO diagram. This is the FEO diagram, and this phase diagram we have discussed, FECO phase diagram. This is in the inverted way it is shown, and we have superimposed this diagram along with the RIS diagram. That is, we can find this is the RIS diagram, and common thing between them is the gas composition, right? So that is there. So from there we know at a particular temperature, we know what is the equilibrium gas composition for the Woodstide iron equilibrium. So this line, you know, 1000 degrees centigrade, that is this point, and this point corresponds to this point into the, what is that called, in the RIS diagram. That is the composition, okay, equilibrium composition. So, and first of all, let's see that by maintaining the shear jet in the blast furnace, that is very important. That is, as we said already previously also, that is, there exists a chemical reserve zone. There is supposed to exist a chemical reserve zone on the top of the isothermal zone in the blast furnace, and if you can maintain that, then your there is the CO utilization obviously will be higher. If you cannot maintain, that means if your O by C is higher, that is you have further, that is the CO required basically will be much higher. Basically, if you have much higher CO compared to that of what is required for the equilibrium. Obviously, first of all, Woodstide reduction has a very low CO utilization efficiency. There is a 70% CO will be in equilibrium. So, if you have a shear jet, then 70% CO in the CO-CO2 mixture will be there in equilibrium, and that CO, when it will move up, it will take out the oxygen from the higher oxide, and then it will come out. So, eventually we have shown that, so your thermodynamic efficiency will depend on that thing, okay. So, basically it will depend on, that is, if you can attain the equilibrium, then it will be the maximum efficiency, obviously. Otherwise, the CO in the gas will be higher than that of the equilibrium requirement. Then that CO, because already whatever the CO after 30% utilization, 70% CO, when it moves up, we have seen, then it is more than sufficient than whichever is required to take out the higher oxide oxygen indirectly. So that's why you will always leave some amount of the CO into the atmosphere. And under a most optimized condition, we have seen direct reduction 54%, indirect reduction 46%. Then also around 40%, 14% CO has to go out of the blast furnace. So, okay, under the most optimized condition. And even if you do not maintain a chemical reserve zone, that is, if the CO in the upper part of the isothermal zone, if the CO is greater than that, whatever is required for the FE equilibrium, then the CO utilization will be further lower. Okay. So, that is by maintaining. That's why, if you can, that's why it is C, where you have two curves is there, one curve is here. You can see at the Woodstide composition, that is 1.06 O by Fe ratio, this line, horizontal line, and your O by C you can find is much lower, okay. In the actual blast furnace, O by C is lower. O by C is lower means your CO percentage into the gas is higher, and equilibrium O by C is here, okay. A to B, if you consider A to B, equilibrium O by C is here, and actual O by C is here. That means you have a more CO into the gas than that of the equilibrium requirement. That is more than that. At 900 degrees centigrade, if you consider the isothermal zone 900, that is 70% CO in the CO-CO2 mixture. So, actual blast furnace, it may be 80%, more than 70%, okay. So, then CO utilization will be further lower, because as I said again and again, whatever the CO is left out after indirect reduction of Woodstide is much higher then whatever is required to take out the oxygen from the higher oxide. So if the CO is further higher than that of the equilibrium requirement, then the utilization will be further less. So CO utilization become less. So if I can move from A to B, okay, that is, then if we can maintain a chemical reserve zone in the blast furnace, okay, then it will be the optimum. Beyond that, we cannot do anything because it is our hand. That is we can achieve the maximum thermodynamic efficiency that way. Okay. So A to B is basically achieving the Wood-tied iron equilibrium in the blast furnace, that is the W point. So we can move from A to B, from here to here, here to here. You can see this dot. From here to here we can move. And how we can move that? Obviously, in that case, we have to increase the reactivity of the iron ore, that is the sinter that we are using. If you have a better reactive sinter, then we can ensure that yes, chemical reserve zone will be there, because iron has to react fast, because within the residence time, because the gas will not stay for a long time. It is a plug flow reactor that way. The gas is moving up, and then whatever the zone length and divided by the velocity, that will give you the residence time into that zone. So residence time into the isothermal zone is not very high. So as a result, what will happen, that is, you may not attain the equilibrium, that is the Fe, Wood-tied Fe equilibrium may not be attained unless you can ensure a very high reactivity of the ore material, that is the sinter and all this thing. So enhancing the sinter reducibility and enhancing the bed permeability. Also, if you can increase the bed permeability, that will also ensure more gas-solid interaction, and if the solid has more reactivity, you can quickly attain that equilibrium. So this thing you have to do if you cannot attain a CRG. Attaining a CRG is essential to increase the thermodynamic efficiency, because we have a limitation, as I said, because Wood-tied iron equilibrium unnecessarily only 30% utilization of the CO. So 70% CO will be there, and anyway it will be there. Even it is more than that, then it is of no use. So we have to think about the sinter reducibility and the bed permeability. Second thing is that lowering the isothermal zone temperature. This is a very unique concept. That is, you can see at 1000 degrees centigrade, what I was saying, there is a 1000 degrees centigrade, as I said, there is the Wood-tied, this is the O by C, roughly you can say 900 or 1000 maybe, there is 1.3. So this is the Wood-tied equilibrium, that is the solid line I am showing, because the isothermal zone temperature is usually 1000 degrees, assuming it is 1000 degrees centigrade, 900,000 degrees centigrade. Okay. So, and that condition O by C is equal to 1.3. Now, if I can reduce this isothermal zone temperature, suppose I have a 700 temperature, then what happens? You are coming here on the Wood-tied Fe line. This is the Wood-tied Fe line. If you reduce the temperature, your O by C basically increases. So that means is the CO utilization increases. CO utilization increases means that is the at equilibrium, less amount of the gas is in equilibrium, less volume percent of CO is in equilibrium. So here it was suppose 70%, here it will be less than that, maybe 60% CO will be in equilibrium and 40% can be utilized. Here only 30% can be utilized, 70% CO will be in equilibrium, right? Here, as the temperature decreases, you can find this line is curving like this. So as a result, at lower temperature, your CO utilization basically will be high. As a result, O by C into the gas, equilibrium O by C ratio will be higher. So you can reach from W to this W prime point. Okay. So this to this point, W to W prime, or you can say B to C. So B to C, that is the lowering the isothermal zone. So obviously, if you can lower the isothermal zone temperature, you can find you can move the W point on the right hand side. As a result, what happens all this thing? As you go from left to right, you can see three lines if you consider. The slope is progressively going down. Slope going down means your coke rate is reducing. You can make a more efficient blast furnace. That is, the carbon rate will be less. As a result, if the coke rate decreases, overall CO2 emission will also be less. Okay? And also, your CO utilization is increasing. Here, what you can find is the CO utilization increases because this point is moving this direction, O by C is little higher. So when the final is emitting, so when the final gas will be emitting, it will also emit at a higher O by C. That means you in the exit gas will have more CO2 compared to CO. Okay. So if it is happening, that means your utilization of CO is increasing. So you are making the furnace more and more thermodynamically efficient. So, okay, so this is a very unique concept, and it can be done basically carbon reactivity by increasing the carbon reactivity. That is, you can use the alkali impregnated coke. Alkali basically increase the reactivity of the coke. Iron, fresh iron also, iron, Ca, calcium can increase the reactivity of the coke. So, you can make the coke basically when you are using the coal for coke making, you can add some amount of alkali in it and then make the coke, that is called the alkali impregnated coke, and in that case coke reactivity increases. If the coke reactivity increases, then why the isothermal zone temperature, how it is decided? Basically the rate of carbon gasification in the isothermal zone, throughout the isothermal zone carbon gasification reaction is going on, right? And so it is an endothermic load. At the same time, gas has a higher heat capacity, so gas will give a heat to, that is the heat to the, what is that called, to the solid. Okay. So, as a result, finally, this dynamic equilibrium, they come to a dynamic equilibrium, that is the, because of this endothermic reduction and heat transfer from the gas to the solid, they come to a dynamic equilibrium and finally attain some isothermal temperature, okay, at a particular temperature of the solid and gas, that is called the isothermal temperature in the blast furnace. Okay. So, and so what we can do if we just increase the more gasification, if you increase the gasification reaction, so endothermic load will increase. So, as a result, gas will lose its temperature because gas has to give some more heat to the solid. As a result, gas temperature will also decrease and the solid temperature will also decrease, and then the isothermal zone can come down to a lower temperature. So, if we can increase the gasification reaction, obviously the isothermal zone will come down because the thermal load of the solid will increase in the isothermal zone and gas will also more heat to the solid. As a result, the thermodynamic equilibrium will come at lower temperature, 700 degrees centigrade say. So, but how we can increase this reactivity of the coke? That is how you can increase this gasification. Gasification we can increase by increasing the reactivity, because if the coke is more reactive, more gasification will go on. So, that can be done by the alkali impregnated coke, and you can use the iron ore coal composite pellet also if possible. That is the iron ore coal composite pellets. What happens in that? That is the iron ore and carbon remain in intimate contact with each other. As a result, the reduction can take place very fast. Why? Basically, any reduction, this type of direct reduction take place by gaseous intermediate, that is the Cu and CO2. So, Cu and CO2 mass transfer is also important. So, if iron ore and the coke particles are in intimate contact with each other, then the mass transfer of Cu and CO2 will be very less, but the mass transfer resistance will be less, because they do not have to traverse a longer distance for the reactant. Okay, they can get the reactant very close by. There is the CO2 is generating by indirect reduction, and that CO2 will get the carbon at the side of this iron ore. So it do not have to move too much of distance. So, because of very close proximity, the mass transfer resistance will also less. As a result, the reaction rate will also increase, and this can also increase this your reactivity, that is the gasification reaction. Overall, the kinetics will be fast and the gasification reaction rate will increase and the isothermal zone will come down. And as a result of isothermal zone is coming down, from this line we know if the isothermal zone temperature decreases, then you can increase the CO utilization, or you can increase the O by C ratio, equilibrium O by C ratio for the Woodstide iron equilibrium. Okay, and CO utilization is increasing. So, that way you can basically increase the thermodynamic efficiency of the blast furnace. Right. And this also has been, that is the Nippon Steel, basically Nippon Steel report has published, and they have tested this also in their simulated blast furnace. They have made a blast furnace, simulated blast furnace, and they are basically all gas injection facility, everything is there. Gas injection facility is there, and a shaft reactor is there, and so gas is moving up. And then they are using the coke also, high reactive coke they have used, and finally they have found, yes, the isothermal zone temperature, that is the decreases, and the CO utilization from the gas analysis they have used, the CO utilization is increases. So, thermodynamic efficiency increases. They have tested their furnace is also some composite pellet also. So that thing they have been done by special binder they have used, and based on that they have tested and found that yes, that is the isothermal zone temperature decreases and the efficiency of the blast furnace increases. So this is from the Nippon Steel report, and you can go through, the whole report is available, you can go through it. Okay. Second thing is that I will discuss about the top gas recycling blast furnace. Basically, it has come after the Kyoto Protocol, and as you know from the climate summit that took place, and in Kyoto in Japan, and then they fixed up there is the CO2 emission, and there is the limit. So, and from that the ULCOS was generated. ULCOS is nothing but ultra low CO2 steel making, and it is a consortium of 48 European companies and organization, and it was birth was 2004 following the Kyoto Protocol. Kyoto Protocol came up in 1996 around maybe 2000, and then Kyoto Protocol come in action in 2005 or 6, somewhat like that. So basically we have to reduce the CO2 emission, and then that's why this ULCOS tried some measures to reduce the CO2 emission from the blast furnace, how we can reduce the CO2 emission from the blast furnace. So one of the major project was there is the blast and the BFTGR, there is the blast furnace with top gas recycling. So that this is the schematics of a top gas recycling blast furnace. What they do here basically, after taking the gas, you clean it, and after cleaning a part of the gas, you goes for the basically gas heater for the stove, and then rest of the gas, what it does basically, it take out the CO2 from the gas, and you can make a CO2 rich gas, and the other gas, that is the CO rich gas, comes here, and you can gas heater, through gas heater you can heat it, and you can purge through two location, either in the shaft wear, it is called the shaft wear, or you can purge it through the that is the tuer, that is the hot tuer, that is the conventional tuer location. And one thing you can see here, basically we can inject the oxygen in place of air, and coal is injected, and it has been tested in experimental blast furnace at Emifors, Sweden. And here the CO2 is separated by VPSA, that is the PSA also it is called, there is the vacuum pressure swing absorption. Here what happens, there is the CO2, and since there is no nitrogen, this separation become easier, because if nitrogen, if you give the air blast, nitrogen is 79 by volume percent, lot amount of nitrogen is there, and the CO2 get diluted into the system, and it will become very difficult to extract the CO2 by VPSA. So VPSA, what it does, basically you have some solid absorbent you keep, it may be zeolite or activated carbon, where you absorb, where basically this type of absorber, they absorb the CO2 preferentially with the CO. So CO2 will be absorbed more into that absorbent, and after that you can use vacuum to extract the CO2, and you can, that CO2 can go for the that is for storage, and the CO rich gas will come, and that you can recycle it. So this is the fundamental aspect of this top gas recycling system. And here you can find, instead of oxygen is given and coal, and one question can come, if you give the oxygen, then obviously the blast volume will decrease significantly, and your that is the wrapped everything will high. But you can, there is the CO gas, basically you can find, you can push through this to air as well as in the sap location, and also the heat capacity of the gas will also decrease if you use pure oxygen. And then to meet up the heat balance in the top part of the furnace, you can have some difficulties. But since we are recycling the gas, this gas is there, so heat capacity is maintained again. Okay, so that way it is there. And also another thing is that oxygen is charged at the room temperature. So that is the thing. So sensible heat, we just extract out the sensible heat of the air blast, then the raft will also be controlled. So these are the thing done. There is the oxygen at room temperature is charged, and the coal at room temperature, and then you recycle the CO rich gas through it, through the two tuers. One is the shaft tuers and the hot tuers. They have used a lot of options, like only through the shaft tuer or only through the hot tuer, and the sometime preheated gas, sometime non preheated gas, and sometime through the both tuers. So all options has been tried out, and then best option they have got it. But it doesn't make too much of difference. But anyway, only one option was bad, otherwise all the other options were good. Anyway, so this is the basically system of the top gas recycling in the blast furnace. Now, the furnace top gas is separated into two gaseous products, as I said. One is CO2 rich and another is CO rich. CO rich gets recycled, okay, through the shaft tuyeres or both, or with and without preheating. Then oxygen is charged through the tuyeres in place of oxygenated blast and at room temperature. This is important. It is sufficient because room temperature, because the blast volume is very less, so you can easily get wrapped. And oxygen injection eliminates nitrogen from the top gas and facilitating the CO2 removal by VPSA. Obviously, if nitrogen is there, as I said, the CO2 will be very diluted, and in that case, separation of the CO2 will be difficult by VPSA, by simple absorption and vacuum chewing desorption. And by this technique, it has been found that we can reduce the 25% reduction in the carbon consumption has been reported, and also 50% reduction in the CO2 emission if you can properly store the CO2. Okay, with the CO2 sequestration, there is a storage of CO2 plus the top gas recycling, is the 50% CO2 emission. There is a reduction in the CO2 emission can be done. So this recycling, one thing is that how much you recycle, that also depends. That is the, here basically the gas partitioning there. Some of the fuel gas is taken out from the gas heater for heating this thing, basically for this thing, and rest of the gas is recycled back here. Now, another very important topic that is coming is the plastic injection in the blast furnace. And so the combustion and gasification behavior of waste plastic into the blast furnace is examined in a in a pilot blast furnace. In what is that furnace? That is the, and two types of plastic has been used. Okay, two types of plastic has been used. One is the agglomerated plastics and another is the solid crust and then crust plastic. There is the plastic which are hard plastic, you can crush it to different sizes and you can use it. And those are the filmy plastic, there is the bag, polythene bag and all these things, they can be agglomerated and then subsequently will be suitable for charging into the blast furnace. And that is the Kane blast furnace 1, Japan. There is the worst plastic recycling was, there is the installed in Natho. Before that they have tested this thing like this, and then through the blast furnace 2 years they have inserted the probe to see the happening inside through the high speed camera, and how they observe that thing, that will just tell about. That is the thing. And then they are gas sampling they are doing, the blast furnace dust, and they have, you can see the gas sampling in different location, in central location, the middle location and the periphery location. All three locations they are monitoring the gas, what type of gas is coming. That is, they basically measure for the different lighter hydrocarbon like C1 to C4 hydrocarbon, methane, ethane, butane, all these things. That is lighter, as well as the tar. This is how much tar is coming, and then the off gas also how much they are coming, they are taking. And then they have rigorously studied, that is the combustion phenomena of the plastic in the raceway. That is very important. And some of the interesting results just I will talk about. There is some important observation were there. They found that coatsar plastic were found to have more residence time in the raceway. If you see the raceway, and then this picture will give a very nice picture, and then you can see then fine plastics and the pulverized coal. If you have a very fine plastic size is less than 0.2 millimeter, that is a very fine plastics, or the pulverized coal, that what happens, some of the partially coals, there is the pulverized coal and as well as the fine plastic, they get an airway out of this raceway. Some carbon, that is the char particle, come out of the raceway, they do not completely burn inside the raceway. That happens, take place. Okay, so those chars are not good, because when they are moving up in the blast furnace, they can block the void and all this thing. So that is they have found. There is the fine plastic also do the similar behavior, like this fine plastic can cross the boundary of the raceway even in the unburned condition. Some char particle can, unburned condition, they can come out and move about, and then they may participate in the carbon gasification later, but they may also block the nozzle and all this thing. And the quartz particle, what happens is that you can find, that is the quartz particle, a part of the coarse and soft particle, what happens? They are also circulating inside it into the, you can see in the raceway they are circulating, and that is in the preheating zone. That is, this is the preheating zone, and outside is the outer raceway where the burning basically take place. So, and this circulation, that is the sum of the coarse particle are moving, a part of the fine particle again find a way out of this raceway. And when the coarser particles are there and the hard particle, there is the coarse particle, coarse plastic, but softer particle, that is means mostly the agglomerated plastics. So, part of the agglomerated plastic, what happens is the agglomerated plastic, they have seen they break, they disintegrate and make the fines also. So, some of the agglomerated plastic make fines, and the fines find a path through the raceway and come out, right. And the coarse plastic and the hard plastic, that is the shredded plastic, okay, hard shredded plastic, they have found those plastic, coarse plastic, they move, they are basically entrapped inside the raceway, and they move in a circulation, they put up in a CSTR type of thing, that is they put up in a circulation loop, right. And as a result their residence time is much higher, so their burning characteristic is better, say burn more, okay. So, that is why the coarser plastic were found to have more residence time in the raceway. So, the coarser particle had better combustibility, basically they do not cross the, that is the raceway. So, they stay for longer time, they fully get combusted inside the raceway and the gas come out, right. That is their findings, okay. And you can see this is interesting diagram. Another thing is that you can see plastic, crushed plastic minus 10 millimeter when the plastic size is bigger, okay, bigger plastic, and this is also agglomerated plastic, bigger agglomerated plastic is this one, and this is plastic in the size range of 0.2 to 1 millimeter, 0.2 to 1 millimeter. So, then this is those plastics. These plastics in the range of 0.2 to 1 millimeter found to be very good, okay. And these are the crushed plastic, that is the coarse plastics, not very fine. So, 0.2 to 1 millimeter, this size is found to be good in a narrow range. This is also called the coarse plastic in a narrow range, 0.2 to 1 millimeter. If your plastic is very big also, then also not good, minus 10 millimeter is there, it is their thing. And the pulverized coal, this is the burning characteristic of the pulverized coal. You can see pulverized coal is also, it is just, this picture has been taken after the plastic has entered into the raceway, just after entering the raceway, this is the happening. You can find the pulverized coal are burning very nicely. Also, the plastic in the size range 0.2 to 1 millimeter are also burning very nicely, right. Whereas, this bigger plastic, both the agglomerated and the crushed plastics, their combustion behavior is not that good. That is much segregated burning here and there burning, not continuous burning like this. So, you can see the burning characteristic is better when the plastic size 0.2 to 1 millimeter or pulverized core, this is there, pulverized core. And how do they calculate the combustibility of the particle? Basically they measure the size, that is, this is the A is basically called the combustion domain. Here basically most of the combustion take place, and this is the preheating domain. Here the particle gets preheated and all these things. So, we found that the solid coarser particle, they reside more on the preheating zone, they basically get up heated, and finally when they come in the combustion zone they burn immediately, okay. So, this region, basically this region, if A to B is more, then your combustibility is more, okay. So, that means your combustion zone, if it is more, then your combustibility is more, because you will combust more, because if this zone is less, you do not have sufficient time for combustion. So, that is the simple reason. So, A, that is the combustion zone should be larger, comparatively larger than the preheating zone, okay. So, this ratio basically they measured, because they can easily capture from the high speed camera what is the ratio of A by B, and then the combustibility of the fuel is decided. And then they have a picture you can find, then plastic, bigger plastic, okay, minus 10 millimeter, they have less combustibility, and agglomerated plastic has little higher combustibility, but still lower, that is the little higher than the crushed plastic of minus 10 millimeter. And then plastic in the range 0.2 to 1 millimeter, crushed plastic in the range of 0.2 to 1 millimeter, they have further higher combustibility. And obviously the pulverized coal has the maximum combustibility. Pulverized coal is more combustible compared to plastics. But if you consider the plastic, crushed plastic in the size range of 0.2 to 1 millimeter, they have higher combustibility compared to agglomerated plastic and crushed plastic of higher size. So that has been seen. And then the tar and lighter hydrocarbons were not observed in the exit gas. They have measured the exit gas, and interestingly they did not find any tar and the lighter hydrocarbons also. And the gas composition was much similar what could have been obtained using the pulverized coal. So that is a very good observation. That is, the tar is not coming, because if tar comes out in the exit gas, that will make a problem, because it can block the further downstream pipelines and all these things. So that is a good thing. And another thing, this plastic char was found to have, another thing is that there is a char that is produced out of plastic. They have found their combustibility is 10 times greater than that of the char that is obtained from the pulverized coal. So plastic char, so once you can make the plastic to char, their combustibility is very high. They plastic char 10 times higher gasification rate compared to that of the coal char. So whatever the char, if the sum of the plastic char come out of the combustion zone even goes up, okay, in the furnace also, then their gasification is so fast, they will basically gasify, okay, and then they will not have some blocking and all these things, chances will be less, because their gasification is much higher. Gasification rate is higher, 10 times higher than that of the char that is obtained from pulverized coal. So these are the very basic reference that you have given. Okay, fine. So these are the reference that you can go through it, and these are all mostly the Japanese paper. So this is two, that is what I say, the blast furnace performance increased by non-isothermal, by reducing the isothermal zone temperature. This is the reference by NATU, Japanese paper. Another thing is that the plastic injection from the Japanese, and then top gas recycling, you can go through this report, that is the iron making, steel making. Okay, so from there. So this is from the basically the MEFOS, ULCOS, that is ULCOS, that is the ultra low carbon dioxide steel production. There is ULCOS publication, that is yeah. So what we see is that blast furnace performance we can increase still. First of all, we have to ensure that the chemical reserve zone exists in a blast furnace, and for that we have to increase the reactivity of the ore, especially the sinter reactivity. And second thing is that we can further improve the performance of the blast furnace if we can decrease the isothermal zone temperature, and that can be done by enhancing the reactivity of the coke. And the coke reactivity can be increased by alkali impregnation, or that is the thing, that is one of the major, and it has been tested into the pilot plant also. And another thing is that top gas recycling. By top gas recycling, we can reduce the CO2 emission from the blast furnace by 50% and overall carbon consumption by 25%. And it has been also tested in a laboratory scale blast furnace in MEFOS. Okay, so that thing is there. And then plastic injection has been demonstrated already in the Keihin blast furnace number 1 in Japan, and some interesting finding from their high speed camera, that is from the photography of the high speed camera in the Tuer location. They have put a high speed camera, and then they have observed some observations which are very interesting. One thing is that it has been found there is the crushed plastic in the range of 0.2 to 1 millimeter. They have the maximum combustibility, and also they interestingly found that in the exit gas you do not have any tar or the higher hydrocarbon also. They all decomposed inside the blast furnace itself. So that is the good thing, and their blast furnace exit gas composition more or less similar to that of the pulverized coal, which could have been using the pulverized coal. So that way plastic injection has been found to be very safe. But interestingly, one thing is that there is the size and shape distribution is very critical, because they have found that a coarse, there is the crushed plastics in the size range of 0.2 to 1 millimeter, they have a more residence time into the raceway. As a result, they completely burn inside the raceway. So important thing is that there is the size and shape of the plastics is very important in the raceway. Okay. So if we can do that, I think there is a scope for further improvement of blast furnace performance. Thank you very much. With this much in this lecture, in the blast furnace lecture, I conclude here, and next on us I'll go to the steel making. Thank you.